All right, happy Tuesday. I hope everybody enjoyed their long weekend. Any questions before we get started? I feel like people are doing pretty decently in here. When I was grading like the quizzes and the homework and the labs, I really thought the answers were thoughtful and deep, so thank you guys for that. So other just kind of things on the horizon, don't forget about your paper topic. So that assignment is in Blackboard. So check Blackboard out. And some of you have already submitted a topic. It should be relatively painless, right? You just kind of type in what you're thinking, and I may put a little bit of feedback. But yeah, I'm seeing good ideas. Just again, ask me if you need help or if you run into problems accessing journal articles, paywalls. I can usually get around them. So that's due next week, I believe. Again, I'm pretty flexible with due dates, but just trying to keep us on track so we're kind of have our topic in mind, and then we can start kind of gathering our main papers that we're going to look at the topic. And right, my ask is, again, we want to look at some sort of primary research. And so some people have asked about like documentaries or whatever other sources you find, that's fine, but then you want to start there and maybe look at what they're sourcing. And then another primary research article that would be appropriate is also like law or case study. So I don't know if anybody is in that direction. I've had a few people like in years past that have been kind of really into like the case study law or environmental law. And so that would be a good primary research. So kind of looking at case studies and breaking down how that went, especially some of the ones historically with like pesticides. I don't have any pulled up at the top of my head, but that's just what comes to mind. And then so other things. Oops, too many windows as usual. So I did find the little baby molecule kits that I love so much. So this is my copy, but obviously I got that like, I don't know how many years ago now. And so you can appreciate, again, the stereochemistry if you didn't already see that. So I have benzene and cyclohexane. So both 6-membered carbon rings, except one is sp3, the other is sp2. And so sp3, again, having 3D structure, sp2 being flat. So you want to be thinking in the correct 3D way. So I've posted a link already to Blackboard this morning. I believe I just posted it to this page, but these are the styles of sets that I like. Like I said, you used to be able to buy them from Amazon. I don't know why they're not available, but you can just buy them directly from their website. So very nice, high quality kits. Those are my favorite for OCHEM. And I would just get the basic set. Obviously, there's like a bazillion things you can buy and knock yourself silly. All right. And so now we're going to be covering our gas law chapter. So I apologize. I know we've had a few people like mix and match classes this year. So I apologize if you've already seen gas laws somewhere else. But this will be a recap. And then if you've taken my Chem 104 with me, this should hopefully feel like a recap as well. But again, we'll get everybody on the same page here. And last week's lab was kind of a good introduction to our gas law chapter. And so let's put ourselves in the right frame of mind. And so a gas is obviously just our phase of matter, and that's our phase of matter where our particles are moving quickly and randomly in a container, right? So our particles are spread far apart. And then the other important thing is when we're kind of laying out this foundation here, we're really talking about this more of ideal gas law. And so right now we're taking kind of a very idealized, oversimplified picture of our molecules, and I'll try to point out where we make assumptions and where, again, a real gas would deviate. And so in this setup, the other factor that we're not taking into account is intermolecular forces. And so that is shown here. And this is, again, essentially what happens, but we're just not accounting for intermolecular forces at all in this ideal gas law. And so our gas particles will just move in a straight line until they collide. So we're just looking at pure kinetic motion. And so they will either go until they collide with another particle or the wall of the container. And so now that gets us into what causes pressure. And so our gaseous atom or molecule exerts a force. So obviously force equals ma. So our tiny gas, right, hitting our surface. So that is our collision. And of course, the measure of the force of that over a certain area gives us our pressure. And so other things to kind of think about, again, just putting ourselves in the correct frame of mind over what is a gas and what is going on. Think about how a balloon stays inflated, right? You physically put air in the balloon, But then that air, right, is bouncing off and colliding. So it's those collisions, right, that are keeping the balloon inflated. And remember, those collisions have to keep it inflated against the atmospheric pressure, right, that's beating back down against your balloon. And so we'll kind of look at that with some experiments probably on Thursday. But again, right, just thinking about this concept of those molecules moving around, non-stop motion, and those non-stop collisions leading to pressure. And so now it gives us kind of the breakdown of the math of that. So force divided by area. And so then the various units of that, so whether newtons per meter squared, so right, force divided by area, which comes out to kilograms, meters times second squared over meter squared. Again, just dividing by area to give us our units of pressure, or joules per meter cubed here. And so again, it's the result of those collisions. And so as you might imagine, again, you can think about inflating your balloon. So the pressure depends on the number of gas particles. So obviously, right, you put more and more air into your balloon and your balloon expands. It depends upon the volume. So right, how big of a container are you putting your air in? Are you compressing it later? And then the speed, which is essentially related to our temperature here. And I'll put temperature, and this is where I'll keep reminding you a zillion times that we're going to be in Kelvin, since we want to relate our kinetic energy to speed, and we want everything to be positive then. And here are our assumptions, and according to our kinetic theory of gases, I'll emphasize this is again ideal. Our collisions of gases with each other and our surfaces are said to be elastic. And again, we're saying they're perfectly elastic, meaning that there's no energy exchange. And right, again, this deviates from a real gas, since when things collide, there's going to be some sort of intermolecular forces, but we're not talking about that right now. We're just saying, okay, they collide elastically. And maybe I'll write that. So no. So IMF means intermolecular forces. So basically, again, we're not accounting for any intermolecular forces. We're just saying everything's perfectly elastic. And then when there is an exchange, that's referred to inelastic collisions. So inelastic would be right where that energy is transferred somewhere else. They showed it in the example of an inelastic collision. Basically, again, that energy has gone into crumpling and not just bounced back out. Yeah.
So the ideal gas law is just purely elastic?
Yeah, so purely elastic, yeah, no energy is lost. And again, obviously, right, that's incorrect. So we're going to get into kind of intermolecular forces later and again kind of address this. But yeah, we're just taking our basic assumptions is that they're always moving unperturbed in a line. All right, so looking again at our factors, which lead to our certain pressure. So again, the higher the concentration, the greater the pressure. That makes sense. So just this is a nice little visualization. So of course the jar on the right is depicted here with more little molecules of air. And so this one is going to have higher pressure. Again, thinking about the greater number of collisions that are going on. And right, I'm assuming they're also at the same temperature. So right now, again, they have the same kinetic energy with them. And then we might imagine, so as our volume increases, then our concentration would decrease. And so again, just to say our molecules does not change, but our volume increases, so concentration goes down. And I'll show a website if you guys haven't ever played with the PhET simulation website, but that's always a fun one. Yeah, some people like it. Like, it is great. You can knock your socks off. And then other things, kind of big picture things to think about is how does pressure relate to weather? And especially when your meteorologist is talking about high pressure, low pressure. And so this variation in pressure in our Earth atmosphere creates wind, and changes in pressure can help us predict the weather. And so usually if you have an area of high pressure, that can be indications of clear weather. So a high pressure system kind of clears the air. And again, right, this is all due to the sun hitting the earth, right, warming up those molecules of air, all those things, right, start these cycle and weather patterns. And then this gets into, I mean, the study of all our ocean currents and all those things. So that's kind of like oceanography and other blends of science. So starting to kind of apply chemistry on a global scale. So imagining our globe is kind of our petri dish. So again, right, your sun is heating up one area of the earth, and that can create our high pressure and low pressure. And then if we have low pressure, that usually indicates there's unstable weather, maybe a storm. And so that kind of, again, gives you an idea. And then other things to note. So the number of gas molecules in a given volume decreases with altitude. So again, right, higher altitude means less molecules of air. And so sometimes people refer to, right, the air being thin. That's just what, the kind of colloquial term is for just saying there's not a lot of molecules of air. And then this goes into, right, other practical applications, like why athletes train at high elevation. So then they can kind of stress their body out and get them exposed to a low oxygen environment and make their body more efficient at processing oxygen. So then when they compete at sea level, then they're super effective. So just things like that. And then other concepts to relate to this chapter are what happens in your ear, especially, you drive around the valley. There are quite a few changes in elevation as you drive around, and maybe your ears pop. And so that's just anytime there's a difference in the pressure across your eardrum. So, right, you have your little membrane here. And so if there's a reduced external pressure and then it's still normalized on the inside, then that can cause, right, your eardrum to bulge, which, causes pain. So that's why people say, right, try to yawn, try to do whatever to try to get this pressure equalized in all your tubes in your face. All right, so now let's look at our units of pressure. And again, we saw this in our lab. And so we saw that our common unit of pressure is millimeters of mercury. And so this is in reference to how you can take the pressure. So you have a vacuumed out glass tube here, and then a pool of mercury. And then, right, you have your atmosphere is literally beating down on that mercury, and then it drives the mercury up that glass tube. And so again, at 1 atm, just our kind of ambient pressure, that would drive our millimeters of mercury to 760 millimeters, or about 29.92 inches. So again, that's just your standard millimeters to inches conversion there, which we saw it in lab, right? So kind of recall last week's lab. So that's what you were doing, right? Doing all sorts of conversion factors. And then I try to mention it while we were doing it, But that was kind of the idea too with our water height column from our lab, right? So we had expanded our gas. Sorry, so this is lab last week, and I apologize, I'm not an artist at all. And so we measured, right, the height of our water column. Again, we're saying, right, how much we move the water. So same thing. So that was the other thing that I wanted to emphasize is in chemistry, generally you want to use like a mercury, what's it's called a mercury manometer or some sort of gas regulator. And so generally you use mercury because it's so dense, right? And so that was part of the conversion factor is that our density of mercury is, I believe it's 13.6 grams per milliliter. So that's why you had to do some division because, right, your height of your mercury is going to be a lot less compared to your height of your water, right, due to their difference in density. So water is a lot less dense, so it can move a lot further, obviously, with the same amount of force versus mercury. So I'm going to try to pull up a picture too, so you can see some of these mercury manometers. And then, so other units of pressure that you'll see is, so we see torr pretty commonly. And so what's interesting is it's the same as millimeters of mercury. So 760 millimeters of mercury, that's 1 ATM, and that's also equal to 760 torr. And so then we'll also see ATM pretty commonly, and this is one you'll want to be in. And so again, 1 ATM, 760 torr. So we have all our conversions between units. Other ones that may come up are pascals. And so 1 pascal at ATM, or excuse me, 1 ATM is 325 pascals. Or you might see kilopascals. So kPa, so that would be 101.325. So that's 1 ATM. Your car is generally in PSI. So anybody know what your car tires are generally at? 51. Other car? Yeah, 32. So I was expecting, mine's around 32. What do you drive? Oh, I'm curious. Oh, nice. That. I wonder why your tires, because generally I thought they'd be around like 30.
Yeah, most tire pressures are like between 30 and 35. Mine's 35.
Yeah. So that's what I was kind of expecting. So right, like just over 2 ATM or somewhere around there. So you can see where 14.7 PSI is 1 ATM. So right, you generally inflate your cars. And then, so we saw torr, and then right, this was from our barometer reading. So this is often what you'll get with the weather report, right? They'll report the pressure or barometric pressure. And again, like we saw in lab, inches of mercury. So again, just have to make our conversion. And then you might also see it in bar as well. That's another one that's maybe used for like weather reporting or sea conditions. And so 1 ATM is 1.013 bar, not to be confusing. Any questions about that kind of so far? I'm trying to find a nice manometer, but it's hard to find a good picture of what you exactly want. But basically, kind of the idea with some of these mercury manometers is it's just this YouTube that kind of shows you your pressure differential between like two places. So when it's like equal, the mercury uh, level will be equal. But kind of the whole point of this and my what I'm trying to show you guys is so when you're doing all this like fancy air-free chemistry manipulation, a lot of time chemists, at least traditionally, use all these mercury manometers since again mercury is so dense, so when the gas blows in and you have to like fill a huge flask, your mercury just goes up, but it'll never bust through. And so if you were to do the same thing or try to do the same thing with water, it's obviously a lot less dense, and if you're not careful, you could suck in your it's called, you would suck in your water bubbler essentially, which I've done from personal experience and seen many other people do. But otherwise, you'd want to use a mercury one. And the reason why we weren't using mercury is because we were doing something super acidic and toxic, so you didn't want to use a mercury bubbler. Hence why use a water bubbler, but not as dense. So physical limitations. And then now I think there's like coming out with new engineering controls where right, they're always trying to get rid of mercury. So mercury gets a super bad reputation. It's really not too bad if you're just like, again, working with elemental mercury, but you don't want to let it loose and let it just start reacting with things, obviously. But people try to get rid of mercury, so now there's like engineering new sorts of apparatuses with springs so that you don't need a mercury manometer. But anyways, you may still see that a lot in practice. All right, so let's just try our simple conversion here. So I'll show our table to relate everything. And so a cyclist inflates her high-performance road bicycle tire to a pressure of 132 psi. So what is this in millimeters of mercury? So let's see your setup. So chat is with it today. And so I'm just setting up my dimensional analysis. So 132 psi. And then, right, these are just relationships. So we can pull our conversion factor from all of these. And so again, we want to relate psi and millimeters of mercury or torr. So there's our conversion factor. So then we have, so 14.7 psi is equal to 760 millimeters of mercury. So it should look like this for the setup, right? Making sure we clear the cobwebs for everybody. And then units cancel. And then what do we get for our final answer in class?
6,824.49
And then so we'll round to 3 sig figs, so 6,800. And well, depending how you want to round that. So if you round this up, so either 6,825 or 24, so somewhere around there for millimeters of mercury. Yes. No, I fixed it. So yeah, depending on how you round it.
I was like, man, I really.
No, no. So yeah, so depending, I was trying to show that there were two different ways to round, kind of depending on the calculator and how you were feeling, and I'm not trying to peg people for like minor discrepancies. Uh, so yeah, somewhere around 6,820 or 30 millimeters of mercury there. Excellent. And then yeah, try to keep sig figs in mind. All right, questions? Feeling good? And so then we saw this again with our lab, right? So again, trying to piece back, well, wow, we were getting all these pieces. But that's all the pieces of data that we were pulling for lab, right? So we needed pressure. So we always need, right, the pressure of our gas. And so that was, again, what you identified last week. You were working to solve your pressure. You had your volume. So again, our eudometer was in milliliters, but then for our equation, which we'll get to, kind of we're teasing it, right? PV equals nRT. We kind of teased it in lab, but kind of building to this. And so with this equation, and why I'm kind of going to emphasize these units here, is when we plug everything in to this equation, and we use, right, that certain gas constant, so 0.08. I usually round it to 0.0821. I think your lab listed as 0.08206, if I remember correctly. But this R is again for these units. So this R is for ATM, liters, Kelvin, right, moles. And so that's why we're kind of emphasizing our units here. And then again, we always have to be in Kelvin when we're talking about thermodynamic related data. So again, pressure. And then moles. So moles is pretty standard. And so like we saw in lab, and we'll kind of see with our simple gas laws, that these properties are interrelated, and so we can change one, and that changes the other ones. And so we'll look at these relationships in pairs first, and then we'll kind of go back to PV equals nRT. But I still want to point out, so I know we've looked at this before, we'll look at it again. So, right, if you just blindly Google your gas constant, remember that you're going to get a bunch of gas constants, and it's all dependent on what unit you're in. And if you remember from last quarter, we did use R, right? So the gas constant came up, but it came up in terms of energy. So you might have remembered this one, right? 8.314, but that's currently not the one we want. So that's for joules, Kelvin, moles. So, right, always pay attention to these units here for your R value so we know what's going on. And then, right, you can just kind of take this in, how the gas constant changes for other units. And then we can find the one that we care about. So this one down here, again, liters, ATM, Kelvin, moles. So yes, that's the appropriate one with the units. And then of course, right, feel free to use a different gas constant if you're ever in a different situation, but just again, be cognizant of your units at all times. All right, so we'll start with these three gases. And so sometimes I try not to, but that being said, like there could be reading questions with like a small bit of trivia. So at least want to take maybe like minor notes or again, kind of bookmark these pages, right? Since I allow you to use notes. And so let's start with Boyle's law. And so Boyle's looks at our relationship between volume and pressure. But let me pull up this PhET simulation. So this should already be linked in the notes. And so it's this PHET Colorado, so they're called PhET simulations. And so their gas one is really popular. Like I said, you might have seen this sometimes. I think this is pretty popular in high school. I don't know if it still is. But if you haven't seen it, or it's always fun to play with again. And so let's look at what we're doing. So let me first put some gas in there. And so what Boyle's observed, so they were playing with these J tubes. And basically with these J tubes, you can pressurize them. And essentially what you can do, okay, we've trapped our gas here. And then in their case, they added mercury to increase the pressure. But essentially that would be the same as adding, right, a piston. And so if we increased our pressure, decreased our volume, right, so our volume went from 1 liter, now we halved it with our piston, then our pressure doubled. And so we can see that again with our simulation. And so we want to we'll hold our temperature constant. And so now let's see, so if we make our little box, and so you can watch, what's fun is you can watch our pressure gauge. So sorry, reset it. So we're at about 10 ATM. So now I'm going to try to decrease our volume by about half. And then we can see how the pressure shot up to 19 ATM. And again, we're holding our temperature constant. So this is just at the same temperature. And then we can watch that again. So now let's like make this really big. So now I've made my container a lot bigger, and we can see our pressure drop there. Right, so then, like I said, there's a link to this. You can kind of play with this on your own all day. And so looking at that, so again, our volume of our gas is inversely proportional to our pressure. And so we kind of have this graph here. But then what do you notice and kind of what happens? What physically starts to happen too at these extreme pressures?
Pressure starts increasing exponentially
And then why though?
because you're approaching zero volume.
So yeah, why can't you get to a zero volume? You're getting there. Tell me.
Because the gas has volume.
Yeah, so right at some point, and so we've kind of been neglecting all of these concepts. Again, with the ideal gas law, we're neglecting that these things take up space, right? We're neglecting intermolecular forces. But yes, at these higher limits, so we have the physical space, so that becomes an issue that yes, they occupy space, so we cannot compress them past a certain limit. And then once we do start to compress them, right, those intermolecular forces come into play, and then they could even start condensing, right, into our liquid then as well. And then obviously, right, you can't really compress our liquid. Yeah. I mean, kind of, except we'd be at even more extremes, right? Like these are extremely high pressures, right? So yeah, at some point, you get to a point where it's going to condense, like we've seen with liquid nitrogen, right? So that's why nitrogen condenses. It's we're compressing, then boom, now it's a gas. And so, or again, you reach right physical limitations. So you just like literally cannot press them down any further. But yeah, I mean, kind of what you're describing as part of that is just, of course, like we as people can only, put down, exert a certain amount of pressure. But obviously, when you start getting into like labs and they're doing these under like extreme conditions, again, you still reach these physical limitations of the size of our atoms here. And then we can break this down into a mathematical relationship. And so looking at this, we have our initial pressure times our initial volume equals our final pressure and our final volume. So again, we're seeing that as pressure increases, then our volume decreases by that same factor. So again, they're inversely proportional. So we're saying if one goes up, then our volume has to decrease, or vice versa. And so things to think about, the application of this is, of course, deep sea diving. And this is also, of course, part of the dangers of deep sea diving. So has anyone been like diving certified in this class? I was just curious because like every year sometimes I have like one or two students that have been like diving certified or like been in the military, so they know exactly about this. And I can share some of their stories. But basically, so we find for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure. So of course, that's quite incredible to think about just from all the water. And so at 20 meters, then the diver would experience approximately 3 atm of pressure. And so the idea, so if a diver holds his or her breath and rises to the surface quickly, the outside pressure drops to 1 atm. So again, we're thinking P1 V1 equals P2 V2. And so our pressure has quickly dropped. So right, that means our volume is going to be rapidly expanding. And so your book here just brings up kind of the lungs here. So it's obviously mentioning, right, why you should be continuously exhaling. But what's the other issue? Why else? Why do you have the bends, or why do you have to rise slowly? It's not just that your lungs might explode, but where else do you have dissolved gases? Yeah, your blood, right? And so your blood has all these dissolved gases. So same thing, right? You want to be exhaling, and you want to make sure that you rise slowly, because otherwise, if you don't give, your body enough chance to get rid of the gas that's also in your blood, then you can have like blood vessels burst and all sorts of things, which gets into, if you're ever bored, right? You can look into the sport of like competitive deep sea diving where people go to like extreme depths, with like no equipment, and then some of them barely survive because they busted, blood vessels from, because right, obviously they're going quickly because they're doing this on one breath, so they're doing what you're not supposed to do, so then they get injured. One of my students, he was in the military and like saw one of his buddies got injured. I think he just like busted a few blood vessels in his eye or something, or he was, trying to get to the surface, rising a little rapidly. I don't know why he was panicking, but he didn't go slowly enough and off gas, and had some minor issues. But obviously, right, this can lead to much larger health issues. Again, you could potentially die. It just depends what bursts. You don't know what's going to burst. But yeah, that's the physical dangers of scuba diving. So that's where there's all this certification and all this training so that you can learn to control all that, right? Have slow breathing, breathe out, not panic, right? So that you're not, because that's the whole point is you can't have your scuba diver trying to panic and get to the surface when you literally have to breathe out and off gas and not rise quickly. All right, so let's do our little practice scenario then. Oh, and so this also explains kind of how our lungs work. So right as we breathe, we inhale by increasing our lung volume. So right, your diaphragm moves down, so increasing the volume essentially. So if your person has an initial lung volume of 2.75 liters and it's at atmosphere, so 1.02 ATM. So we're saying, right, imagine that moment our diaphragm is contracted, right? It's just made our lung volume bigger, but right, it's just a second before any air has entered. So what is the new pressure in the lungs? So before any air, if we could pause that moment. And so for these problems, I know we're just emphasizing the units, but for these kind of like direct relationship pairs, the units don't matter so much as long as they match. So technically, right, we could be in torr or milliliters or any other units of pressure and volume. And so then chat hasn't given me an answer. Let's see what you've done in class here. So just setting up our initial conditions, so 1 ATM, 2.75 liters, and again, they gave it to us in kind of our standard units anyways, so that was kind of nice. And so then solving for x, so what do we get for x then of our pressure? I got 0.863, and chat just came in and they agree. And then double check your sig figs, everybody. So 3 sig figs, so it looks good here. And so again, right, this is showing us, yes, that's why air was going to rush in. So you've now created a kind of mini vacuum in comparison to our atmospheric pressure. And now you'll get fresh air in your lungs. That's pretty exciting. All right, this is probably a good time to take our little 10-minute break. So maybe come back at 11:55-ish or so, and then we'll look at Charles's law. And I'll try to hand back. I have quizzes, and like I said, I've been making my way through the labs. All right, did we make it back from break?
What is the point of paper? What are we arguing?
Whatever you want to argue. All right, so as we make our way back, so we could kind of play with our little PhET simulation again and put us in line for Charles's law. So let's look at what Charles's law looks at. So now we're just looking at our volume and temperature relationship. And so the key of Charles's law, and again with any of these kind of two-pair relationships that we're looking at, is that we're holding the rest of the variables constant. And so we're holding a constant pressure, and so it's going to say, okay, if we're going to keep our pressure the same, then as our temperature increases or decreases, right, then our volume will adjust. So let's look at that. And so I have our little simulation up, and so it says hold constant. So now I'm going to pick pressure, and it should change with our move the volume. At least I hope that's what happens. And so now I'm going to cool it down. And so notice, right, as you cool it down, it's keeping that pressure constant. So then the volume is decreasing. And then now we can do the opposite. So again, watch it hold steady at 13.9. So increasing our temperature. And then we can see those molecules moving faster and our volume again increasing, right, as our temperature keeps rising. And so again, right, that makes sense. So we're holding our pressure constant, and so our volume is continually increasing. Eventually you'll break it. All right, so that makes sense. And so now we can say that they have a direct relationship. So meaning, right, as our temperature increased, then our volume also had to increase. And again, I'm just emphasizing that we're holding our pressure constant for this one. And then, so this is one where the units do matter. So temperature, again, has to be in Kelvin since it has thermodynamic relevance. So we want to go from a scale of 0 and positive, right, and obviously not experience negative numbers. So then we can set up our mathematical relationship. So V1 over T1 is equal to our final volume over our final temperature there. And so like we saw, again, with our kinetic molecular theory, as we're increasing the temperature of the gas, we saw how the average speed and, of course, average kinetic energy, and we could even think back to the formula, right? Kinetic energy is 1/2 mv squared. So again, just kind of keeping that in our mind. And so our kinetic energy is increasing, and like we said, to keep our pressure down, then we have to increase our volume, right? Spreading our surface area over a larger space. And then we can see this graphically. So again, this tracks pretty nicely. Just watching our pressure, or our temperature volume relationship here. Oh, and we can, sorry, another formula we might want to think about is kinetic energy is 3.2 kT. Basically just that it tracks with temperature, right? So we're just saying that our kinetic energy is a function of our temperature, so both these are relevant. So again, right, they're just kind of reminding us what's going on. our gas is moving faster, and that's a function of our temperature. And so again, right, this tracks nicely mathematically, and then obviously we have these dotted lines since eventually all our gases condense into liquids. So again, that's kind of the difference with kind of our ideal situation versus a real gas. So again, our equation kind of breaks down since they condense. So we again have those physical limitations essentially. So again, at extreme conditions, right, our equations kind of break down from the true situation. And so like I said, I'll bring some more things on Thursday to kind of help with this so we can look at just kind of how this is. Actually, let's do a video. We'll watch the video, but then I'll bring in what I call the baby version of this experiment on Thursday.
Hi everybody, I'm meteorologist Jay Burschback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel. I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up. Okay. So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right. So it'll take a few seconds here to get the water warmed up inside the barrel. But to give you an idea how big the flame we're going to work with. There's a good sort of jet of steam shooting out, and we're going to try to capture that by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to just spin it down. Rotisserie. Well, the first thing we should hear are a couple of ends of the drum popping in.
There we go.
The ends going in. There's the other end.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside has cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can. Or if you ever rinsed out plastic milk jugs,
sure,
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure, yeah, no one, you know, having that blowtorch,
blowtorch is
for the
probably
experts like you.
Yeah, Yeah, so I like that video. So I don't know if you guys have kind of noticed the milk jug thing at home that he kind of mentioned. You'll ever never rinse out some milk jugs. I totally noticed that if I do that. Like I said, I'll bring in some demos. I didn't want to get too distracted today, but we'll save Thursday for kind of playing with some of this stuff in person. So I'll bring a mini can and we'll crush that, right? But again, just kind of thinking about what Charles's law is telling us. So it's essentially just reminding us that, right, as our temperature of our gas increases, then again, our particles are moving faster, more collisions, greater force. And so we could take a balloon, and this is hopefully my plan for Thursday to again play with this, is take a balloon, put it in boiling water, and then see that balloon hopefully get, right, a little bigger. And then usually you see the reverse, and I like to do the reverse, and I'll bring it some liquid nitrogen, because obviously it's more extreme with liquid nitrogen. And again, right, slowing down those gas particles, and you can see, right, obviously your balloon gets smaller and smaller. And of course, right, obviously we're not doing a great job of keeping our pressure constant, right, in these scenarios, but we can imagine that, of course, right, our volume would have to keep expanding to accommodate this one, and then again our volume would, and we see our volume decrease, right, on our balloon, but again I'll do these demos and we'll see that. Just our balloon decreasing, and sometimes you can even notice, if I do it with liquid nitrogen, kind of the air inside condenses, and you can see kind of the liquid in there, in that balloon. And so it's just pretty amazing. And again, kind of watching that video, just kind of recap in your mind, right, what happened. And kind of the key and how they made it so dramatic is they replaced it with water, right, taking advantage of the fact that they were going to heat up that water and kind of get rid of any other, right, air particles and anything else, so that it's hopefully just a lot of water molecules to get that dramatic conversion. And then again, taking advantage that water boils at 100 degrees Celsius, but then freezes at 0. So pretty accessible temperatures. And then of course he sealed it, right? So that was the other point, is they sealed it really tight so that you can't have moles going in and out. And then again, right, as that water, so was previously expanded, then it cools back down as they cooled it. So then, right, imagining the water, that's supposed to be my water condensing, leaving a vacuum. And then right now there's no more air to hold it up against the atmospheric pressure. And so that's why, of course, it started collapsing in on itself. But we'll do it, like I said, on Thursday and play with a few pressure things then. All right, so let's try the math now. And so again, I'll remind ourselves that we need to be in Kelvin. And remember, the temperature Kelvin is equal to temperature Celsius plus 273. And technically 273.15, but really, I feel like we don't generally measure temperature that precisely, so I always round to 273. All right, so try this one. So our sample has an initial volume at some temperature, and then we submerge it in ice water at 0 degrees Celsius. Our new volume is 2.57. So what was our initial volume? I'll just rewrite the formula. All right, how does our setup look like? So, right, we have our initial volume, X for our temperature, then 2.57 liters, and then we had to convert, right? So, luckily this one was easy, so 273. Again, you could use the 0.15, but really won't make too much of a difference. And then do our cross multiplication. Sorry, I didn't pull up my calculator yet this morning. Try to find it. And so what do we get for X? What was our initial temperature in Kelvin? What was it? 297 Kelvin. Excellent. Did we all get that number? And so right, again, just always, these are good problems to kind of sanity check yourselves on. So again, just kind of make sure, does it make sense, right? So yes, we expected it to be a slightly higher temperature, so that kind of makes sense. And then it asks for it in Kelvin and Celsius, so then we just need to subtract 273 from that, so it looks to be about 24 degrees Celsius for our initial temperature. Questions on that one? Hopefully feels relatively straightforward on these. All right, let's look at our next relationship. And yeah, it shouldn't matter whether you flip kind of temperature or pressure, since it's just a relationship for these. So that's good. And then kind of our last, again, pair that we'll look at specifically are volume and moles. And this one I feel like is pretty straightforward. And so now we're saying that our volume is directly proportional to the number of gas molecules as long as we're holding pressure and temperature constant. So let me find our simulation again. And so this makes sense. So let's see, I'll try to hold pressure constant. And so now if we add, oops, I exploded it. Oh, that's annoying. Sorry, let me turn off the noise. All right, so now we'll put some starting moles in. So again, holding pressure constant. And, oh my goodness. Sorry, I keep exploding our little container for some reason. So there we go. If I'm a little more cautious. And so again, right, all we're showing, okay, I'm pumping more molecules of air in, and then we're holding our pressure constant. And as we're doing that, our container, again, keeps expanding, right, to keep that pressure constant there. And again, I feel like that's pretty straightforward, right? We're holding pressure and temperature constant, so obviously more gas means larger volume. And then again, for our ideal gas law, equal volumes of gases contain equal number of molecules. We're going to see this isn't quite true in practice, but it is pretty close. And then again, mathematically, our setup is V1 over N1 is V2 over N2. And again, a direct relationship between these. So as we again increase our N, then we increase our volume, or vice versa, holding the other variables constant. And so it tracks linearly, makes a nice graph relationship like we would expect. So again, it's proportional to the number of gas molecules. Again, that makes sense since that's increasing our number of gas molecules, so more collisions. And so to keep our pressure constant, then again, our volume will increase. All right, so let's again look at this scenario. And so let's read through this one. So now we're doing a kinesiology research study, and we're looking at a male athlete, and they have a lung volume of 6.15 liters during a deep inhalation, and his lungs contain 0.254 moles of air. So during exhalation, the lung volume decreases to 2.55, but then it asks how many moles of gas does he exhale? So how would you figure this out? And then we can rewrite our equation if that is helpful for people. So how's this one going? So what are we trying to solve first? What are we finding? So N2, which is, so yeah, in the lungs. So that's just what I wanted to emphasize. So good. So then, yeah, tell me what you found. So let me set it up. So 6.15 liters, 0.254 moles initially is equal to 0.255 liters over X. And so then what do we get for X? 0.105, and so that's moles, and again in our lung. And so it's asking for exhale though, so we just need to do a little subtraction. So then our initial volume, so 0.254 moles minus what we exhaled. And so what does that give us for the final moles exhaled? .149. Excellent. And I don't see chat confirmation, but just making sure they're still with us. Excellent. So did we all get this? Sounds good. All right, not too bad. So hopefully these equations kind of feel good. All right, so let's do a quick, I call it a very minor baby derivation. And so now what we want to kind of look at is, well, where did all these formulas come from? And then kind of how do we rederive them? And so let's go back to our ideal gas law, or this relationship, right? So we have this PV equals nRT equation, and let's just again redefine all our variables. So P for pressure, again in ATM, V for volume, liters, N moles, R is our gas constant, so that's our kind of key here. So 0.0821. And then temperature in Kelvin. And so this is the key point, is so now we can rearrange this equation to set to R. So that gives us, right, our PV over NT equals R. And so now we can say, well, this is true, right, for any set of conditions. So you can have P1, V1 over N1, T1. And again, that's equal to any other set of conditions. So P2, V2 over N2, T2. And so this is basically, right, our key relationship then, or some people kind of call this our combined gas law or something. And so this is a good reference point though. And so what we find, right, so let's go back now to our other dual relationships. So we had started with Boyle's, right? So we said Boyle's was just looking at pressure and volume, and we held temperature in moles constant, right? So now let's go back to our baby derivation. So again, Boyle's, we hold temperature and N constant. So what I'm showing you is now we can rederive all our gas laws. So starting with this combined one, so P1 V1 over N1 T1 equals P2 V2 over N2 T2. And then we can cross out any variables that hold constant. So again, in the case of Boyle's law, it explicitly states that the moles and the temperature are constant. And so that gives us back out, right, that simple formula that we had been presented initially. And so then we can do the same for our other relationships. So looking at Avogadro's again, so we held pressure and temperature constant. So temperature and pressure are constant. So again, right, we can start with our combined gas laws. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay, so Avogadro said let's hold temperature and pressure constant. So right, that eliminates those variables. And then we get back out, right, our Avogadro's relationship of V1 N1 equals V2 N2. And then we can do that for the last law we looked at. Where did it go? Where's Charles? There it is. So Charles, again, we said we hold pressure constant. So now let's just do the same for Charles's law. So Charles, we said, so volume, so that means pressure was constant. and moles constant. And so again, we'll just go through one more mini derivation. And so the other time that this whole combined gas law formula is useful is if you have like just one variable is constant and maybe you have 3 unknowns or something, or even if you had all 4, right? So again, you can kind of adapt it to any scenario. So then Charles, like we said, so pressure is constant and moles is constant. And so we get back Charles's law of V1 T1 over V2 T2. So that's super useful. So that being said, right, on an exam, really the 2 relevant formulas are PV equals nRT, right, since that's our kind of ideal gas law. And that's is if we don't know, right, any one of these variables, so we can sub out and solve. Or if we're comparing, right, initial conditions versus second set of conditions, then we're going to want to use this gas law formula. Does that kind of make sense? Kind of when to use either one? And right, we can always start with this kind of combined gas law, and again, just eliminate the variables that are held constant, and then we can rederive all our specific ones. So hopefully we feel pretty good about that. So then that brings us to our ideal gas law. So now our combined relationship. And again, we've kind of gone over this, so we're just re-emphasizing again that we're in ATM liters mole, which gives us that R gas constant. And again, I'll rewrite it 0.0206 is the other number we'll see. So they're same thing with rounding. Temperature in Kelvin. And then again, just showing how we can derive all our other gas laws. Oh, other things to note, sorry, while we're looking at this before I forget. And so what do you notice about pressure and volume? So what side of the equation are they on? And what did we say about these variables? So are pressure and volume, are they directly and indirectly related? Inversely, right? And so now we can see why that is. So again, same side of the equation. That means that they're inversely related. And then looking back at our kind of direct relationships, so maybe volume and temperature, for instance, right? Opposite sides of the equation. So that means those are directly related. So again, as one goes up, then so must the other if they're directly related. And then we could say variables like, so looking at moles and temperature, right? Again, they're on the same side, so these would be inversely related. So that's how you can kind of break it down when looking at these variables. All right, so let's try this practice problem then. So see if we can calculate our volume occupied by 0.854 moles of nitrogen gas at 1.37 ATM and 315 Kelvin. then we can just plug it in. So PV equals nRT. So right, we could rearrange. So V equals nRT over P. So then just plugging in numbers. 0.0821 temperature, and right, they gave it to us in Kelvin, which was nice, but just always read carefully. And so what do we get for our volume then? So 15.9 liters. I see chat got the same, and yeah, 3 sig figs is good for that one. Any questions? Fairly straightforward, hopefully. Again, just make sure you're plugging and chugging along so that you feel good about this. And really, this unit should hopefully be easy. And really, I think the hardest part is just double check that your temperature is in Kelvin, right? All your units are matching up, so you're not doing anything silly. All right, so then that leads us to our standard condition. So this is just definition now. And so, like we just finished covering, obviously our gas and our volume could be at so many different pressures, temperatures, conditions. And so that means chemists agree to a standard set of conditions to easily report measurements. And so this is called STP, or standard conditions. And so our standard conditions are 1 ATM, 273 Kelvin, or 0, but we'll keep it in Kelvin. And then that gives us 1 mole, and that's saying that 1 mole occupies 22.4 liters. And so that's super convenient, and I would think about, right, other conversion factors you can use with that. What are you saying? And so what you're saying is you have a mole of this, which is 6.022 times 10 to the 23rd atoms or molecules of gas. And again, that occupies 22.4 liters. So little shortcuts there of proportions that could help you with problems. You can plug it in for yourself too and double check. Yes, 22.4 liters. So that is, again, just showing how everything works out mathematically. And so then, again, we're saying this is where we make our idealized assumption that every mole of gas is 6.022 times 10 to the 23rd molecules. And so it is saying that we should recognize the difference in density. So it points out different masses. So then this is really saying they have different densities. But we're still assuming that, again, they're occupying 22.4 liters. And then obviously we could get, right, the molar mass and kind of compare. So helium's going to be lighter than xenon. And then, right, xenon is heavier than methane. So just important to recognize that at least. All right, other concepts that we want to look at are partial pressures. And so many gas mixtures are actually mixtures of gases. So air is obviously the one that we're most familiar with. So it's 78% volume of nitrogen, and then 21% oxygen, 0.9% argon, 0.04% CO2, and then, right, other trace gases. And so we'll kind of see how to treat this. And so essentially, right, what it comes down to is, again, the identity of the gas doesn't really matter. And so even though it's a mixture, then our pressure, volume, temperature can all be kind of treated as one. So as long as we know our total moles, then we can determine our partial pressures. All right, so let's look at all in detail what this means, or we'll see how far we get to. And so Dalton's law states that our total pressure of a gas mixture is the sum of the partial pressures. And again, we're assuming that our particles have negligible size and they do not interact as we stated. So again, that's just going with the ideal gas, what we mean by that assumption. And so again, we're saying that particles of different masses have the same average kinetic energy at a given temperature. And since the kinetic energy is the same, then our total pressure is the same. So again, we're just saying, right, identity doesn't really matter the gases for our purposes. And so looking at a mixture of gases, so if we wanted to look at just a single gas in our mixture, like in air, then we'd be calculating its partial pressure. And so we can calculate our partial pressure either by knowing the fraction, or, right, we're given basically the percent composition and the total pressure, or we could figure out our percentages of moles. So if we had the number of moles of gas in a container of a given volume, and if you know it, so we could calculate it. And so again, all we're saying is, right, we can add up all our partial pressures of all our gases to get our total pressure. And so again, all we're saying is it's dependent upon the number of moles, and so then it's additive. So this is just, again, proving why it's essentially additive. And so then that means you'll probably want to figure out the mole fraction. So our partial pressure of our component is its either mole fraction or percentage, again multiplied by the total pressure. And so going through this one, so we're given a 78% composition in air, and so then we can take our percentage, so just moving over our decimal point, so 0.78 times 1, right, because this is our total air pressure. So figuring out, again, our mole fraction. And so then multiplying this, we find that nitrogen has a partial pressure of 0.78 atm. And then we can repeat this. So this is just from up here, right? So multiplying each one of these percentages. So then that means we have 0.78 atm of nitrogen, and then roughly 0.78 atm of oxygen for its partial pressure, and then of course 0.009 atm for argon, and then getting even smaller, so 0.0004 atm of carbon dioxide there. So again, just kind of keep track of your total number of moles there. And then you can see how you can add them back up and get our total pressure. So right, that could be a problem too, is like, hey, we hear the number of moles of each one, so calculate the total pressure of a system. All right, so let's try this one. So we're looking at a 1 liter mixture of helium, neon, and argon. And it has a total pressure of 662 millimeters of mercury at 298 Kelvin. And so it gives us the partial pressure of helium, so it's 341. The partial pressure of neon is 112. So what mass of argon is present? Not a homeless person, but a car lost like their giant metal rod or something apparently. Anyways, entertainment of the day here. So how are we doing so far? What do we need to start with first? So what do we start with, right? We have our total pressure, our partial pressures. They're asking for mass. Where should we start though? So what can we calculate first just from Dalton's partial pressure law? Or argon, you mean? Yeah, so let's start with that. So they told us the total pressure. It's a 3-gas mixture. We have 2 of them. So let's just find, just step 1. So find our partial pressure, or pressure really, of argon. So taking 662, again our total pressure minus our mixture components, so 341 and 112. And so then I believe that gives us 209 millimeters of mercury for a pressure of argon, correct? Okay, excellent. So just want to make sure we're all following along. Because these partial pressure problems, they always confuse people. I think there's just a lot of information kind of floating around. But what we're trying to find is kind of what's relevant to our question though, right? So we're only asking about argon. So now we're kind of thinking of, well, I'm probably going to need PV equals nRT, right? Because that's always kind of our go-to, especially when we're not comparing, right, initial and second set of conditions. We're just trying to find something. So now I'm just seeing, do I have all my variables? So now I have pressure. We'll need to convert this. So 209 millimeters of mercury divided by 760 to give me my new pressure. So I think I have that down as 0.275 atm, correct? Just double check with me. I see chat has a final answer. I'm still working there. And then volume. So our volume is still 1 liter though, right? So it's still occupying this. So 0.275 atm times our 1 liter equals, so we're trying to solve for n, right? Because we're trying to get my number of moles. R is my gas constant. T, they gave it to us, so 298 Kelvin. So this looks good, right? So now we can solve for moles. And so what do we get for number of moles? Just moving around our variables. And so I'd see it in the chat, 0.0112 moles of argon. So other people got that, good. And so then, right, last step is just doing our usual moles to mass conversion. And I have mole highways if people need mole highways or other kind of cheat sheets to jog our memory on how to do these sort of calculations. Otherwise, right, use your dimensional analysis. So finding our mass of argon, so 39.94 grams per mole. Moles cancels, and then that should leave us with 0.449 grams of argon. So let me know if you got that. So that's what I have from my notes, and I think chat agrees. And then did we all get that in here? Is everybody on the same page? Oh, and we are out of and over time. So yeah, that's a good place to end, but we're going to continue kind of with these partial pressures. We'll look at our gas issue, and then we'll do some more practice on Thursday, going through the rest of the chapter, and kind of we'll keep practicing. And I'll bring some fun stuff too, but again, just keep practicing. As long as you're plugging along and plugging away at your calculator in class, you should be good with this chapter. So just keep it up. All right, I will see y'all in lab. Lab should be fun. So we're doing TLCs today, so the printout is there. So I will see y'all in lab. And if there are any questions, just email me. Yeah, we can start a turn-in pile.